Hi guys, and welcome to the first lesson in topic 5 about endothermic and exothermic changes in chemical reactions. And what we're looking at today is we're looking at specifically the energy changes in a chemical reaction and what happens to the energy and that involved in those changes, where it goes and where it comes from. We're going to look at some examples of what an exothermic reaction is and some examples of everyday uses of those, and we're going to do the same thing for the endothermic reactions as well. Now, you might already have a good idea about exothermic and endothermic reactions and their uses, and that's fine, but hopefully we'll learn something a little bit new. But this is just a very easy introduction to topic 5. It starts off quite easy. There are some difficult topics which are the higher tier things, but we will point those out. So the first part that we're going to be learning about today is suitable for chemistry and for the combined sciences at both higher and foundation tier. So the first thing we need to cover is the law of conservation of energy, which is one of the fundamental laws of all of the sciences. It's especially relevant for chemistry and physics. And what it says is energy cannot be created or destroyed. So the energy we have around us, we can't create or destroy it. When we talk about generating electricity, we are generating electricity, we're making electricity, but we're not creating energy. What we can do though is we can change energy from one form into another, and we can transfer energy from one place to another as well. And an example is electrical energy. It can be converted by a light bulb into light energy. Okay, and that light energy will go off and that will hit objects and be absorbed by those and cause vibrations. So that's kinetic energy or heat energy as well. And that will dissipate off and spread out. But we can trace that energy, and it gets quite complex about where that goes. But you just need to know that energy can be transferred and changed. Another example: batteries are a store of chemical energy, and that energy can be converted into electrical energy and then transferred to, say, a buzzer, for example, which will transfer or change it into a sound. Same thing happens in your phone, in your the speaker in your phone. The battery in your phone contains chemical energy. It is changed into electrical energy, which travels to the buzzer or the speaker, and then that's converted from electrical energy into sound energy, which reaches your ears and causes vibrations or movement in your ear, kinetic energy. So each of these steps, the amount of energy, total amount of energy, must stay the same. We can't create it, we can't destroy it, we can't lose it. It can only be changed from one form into another. Now, this is important for chemical reactions because chemicals contain energy inside the bonds. Okay, so chemicals contain energy inside the bonds in between the different atoms in the chemical, and different chemicals contain different amounts of energy. Okay, so different bonds contain different amount of energy, and this is something we'll look at in a future lesson. So if we take a reaction, for example, A plus B makes C plus D, where A and B are the reactants and C and D are the products. If the products contain a different amount of energy to the reactants compared to the reactants, so if they've got a different amount of energy, then there must be something that energy is doing. It's either going somewhere or it's coming from somewhere, and we need to be able to explain what has happened to that energy and explain that difference. And it's easier than it sounds. So to start off with, exothermic reactions, which is one of the types of reaction we need to know. This transfers energy to the surroundings, to whatever is surrounding it. That could be your hand, it could be a beaker, it could be the liquid the reaction's happening in. And this energy is transferred in the form of heat. You can also have reactions that give out energy in the form of light and sound, but technically, you could argue they are not exothermic because thermic stands for heat. Exo, exit, and thermic, talking about heat. Obvious examples of exothermic reactions are things like combustion, so burning something. So if you set fire to something, you've got a wood-burning stove, or you've got a gas hob. Those are examples of combustion, and we can tell they give out heat because they warm environments up around them. For example, a pan or the room. Hand warmers, the little gel hand warmers that you might get, snap a little disc or a little plastic pellet inside them, and they start to heat up. They're also an example of hand warmers. The reason why I put those in bold is because they are two examples of exothermic reactions. The syllabus, the exam syllabus, AQA syllabus, specifically mentions, so you should be aware of those are examples of exothermic reactions. They also include neutralization reactions, so when you mix an acid and an alkali, if you put a thermometer in there, you will notice the temperature goes up. And it also includes many oxidation reactions as well. Oxidation being where something reacts with oxygen, combustion being an example of oxidation reactions. Oxidation reaction is also where something will lose electrons as well, and sometimes you will notice they also have heat gain, but we're focusing specifically here on reactions where something is gaining oxygen, reacting with oxygen. And all of these reactions, one thing they have in common is they feel warm. The temperature of the surroundings goes up, so if you were touching the hand warmer, your hand is the surroundings, the temperature of your hand goes up. In a combustion reaction, the air around the combustion reaction heats up, the temperature goes up, the energy is transferred into the air. In a neutralization reaction, if we get an acid and an alkali and mix those together, the heat is transferred into the water that the reactants are dissolved in, and then into the thermometer, which registers the change. Now there are some uses of exothermic reactions that you need to be aware of as well. And hand warmers are the first one, so you need to know hand warmers are exothermic reaction and a useful one, and you can think of reasons why they might be useful, especially if you're doing DV or something like that. If you're out in the wilds and it's very, very cold, you might need a hand warmer to keep your hands warm and stop you getting frostbite, for example. But they generally use two liquids and they react together in an exothermic chemical reaction and they release heat. Another example are self-heating cans of drinks. Now these became kind of like big and a lot of advertising done on them. I want to say about 2000 and probably about 2012 or something like that, maybe 2013. They never really took off because one of the problems is you'd have a can of coffee with a little self-heating mechanism, which was a chemical reaction, and they worked really, really well on a warm day. But if it was a cold day, say it was about freezing and you had the can at about freezing temperature because you were outside, they would tend to only warm up the can to about 20 degrees, so your hot drink would be kind of a tepid, lukewarm drink, so it wouldn't be very much fun. But it's on the syllabus again that you need to know self-heating cans of drinks, even though they've kind of died a death. In these cases, for the exothermic reaction, the chemical reactants, so what we're starting with, the chemicals that are going to react together, they contain more energy than the products do, what gets made. And the energy difference escapes as heat. So because their chemical reactants have got more energy than the products, that difference in energy must escape, and it escapes as heat. And here's a little example. So if the reactants in green contain 200 joules of energy and the products contain 50 joules of energy, then the products contain 200 joules minus 50 joules, 150 joules less energy than the reactants did. Okay, so they've got a energy difference of 150 joules or minus 150 joules. This energy must escape to the environment as heat. It can't just disappear, we can't lose it, we can't click our fingers and magic it out of existence. It goes somewhere, so it goes somewhere as heat. Now, endothermic reactions. They're like the opposite of exothermic reactions. Instead of giving out energy, they take in energy from the surroundings. And this causes the surroundings to lower in temperature, so they feel cold. Some common examples are cooking food, so this is often mistaken as an exothermic reaction. If you're using a gas hob, the burning of the gas is exothermic, yes, but you're using that heat to put into the food, and the food temperature is not as hot as the flame temperature, and that is because you're doing something with the chemical bonds and you're doing something with the chemicals, and the products have got more energy in them than the reactants. Another example is thermal decomposition, and again this is bold because it's mentioned in the syllabus explicitly. Thermal decomposition is if you've got something like calcium carbonate and limestone and you heat it up, you form calcium oxide and carbon dioxide. Now you might be able to create your own symbol equation for that. So I'll give you calcium carbonate you should be able to work out if you've got a little bit of knowledge of topic 2. So if you want to give that a go, work out the balanced chemical formula. That's a really good idea to practice some of your skills from the other topics. Another example of an endothermic reaction is cold packs for sports injuries. So you might have used these. Again, there's different types. There's the ones that you get out of the freezer. I'm not talking about those. I'm talking about the ones where you've got like two liquids inside a pack, and often you have to squeeze the pack to burst the inner pack, and the two liquids mix and it gets very, very cold. And they're very useful if you're going out and doing sports somewhere where you don't have access to a freezer, for example. And in these cases, for all endothermic reactions, the products are going to contain more chemical energy than the reactants. And that energy has got to come from somewhere. You've got to take in that reaction energy from the surroundings. And that results in them feeling cold. That's why when you get the cold pack and you snap the pack and you put them on your injury, it feels cold, because it's taking the energy it needs for the chemical reaction from you, from your skin, from your body, and that's why they feel cold. Now the summary. Energy cannot be created or destroyed, it can only be changed to form. Okay, so in a chemical reaction we can't just get rid of the energy. That's the difference between the chemical reactants and the chemical products. Exothermic reactions give out heat to the surrounding. They warm things up. They increase the temperature. Endothermic reactions take in heat from the surroundings, so they get colder. And examples of exothermic reaction are combustion, neutralization reactions, hand warmers in self-heating cans. And examples of endothermic reactions are thermal decomposition reactions and cold packs. Now in the next lesson we're going to have a look at an example of how we can do a practical to decide whether things are endothermic or exothermic reactions, but you can probably have a good guess and a good workout of why those things are like they are. Anyway, hope you liked the video, guys. Please remember to like if you do. Please remember to subscribe if you've not already done so. Share it, please. More people get to see this, the better. And if you've got any comments, please leave them in the comment section below. I look forward to reading them, and I will respond to them if I think they are a question about chemistry, or I think they're particularly amusing. Okay, take care, guys. Enjoy your lovely summer as it started to be now in late May in England. Okay, bye bye.